You do abandon us at every opportunity. Okay, I feel like I'm forgetting something, but I probably will remember it at the last second. According to GPU update, refresh your audio settings. It didn't capture my disrespect. Aww. A GPU update messed with their audio settings? I don't get how that works. That's annoying. I don't remember how I was disrespecting you. I believe that I was. It's getting set up. 2 minutes? Okay. Let me hop into Discord. Use a DAC. I can't deal with an update. Oh, I have a DAC also. I don't think I did anything special with drivers though. I don't know. It's not a very fancy one. Well, it's kind of fancy. I don't know. I could believe that a DAC would get messed up. I don't think mine would, but I can see how that might happen, I guess. To be honest, there's no reason for me to have a DAC though. I bought it back when I had an actual job and just had spare money. I was like, oh, let's give me like a 1% improvement in my audio. Let's do it. Not only for streaming, it's for actual radio stations. Mine is for music, but you really don't need them. Like, they don't really improve your music by enough that a human can really hear. So unless you have like actually have static from connecting it directly to your motherboard, there's not really a point for me to have one.
John.
Oh, hey.
Happy Saturday.
Happy Saturday. Slim, thank you. Sounds good, Skirtle. Talk to you soon. Slim, nice stream. Welcome in, everyone. This is a general relativity day. We got 10 bucks on the horn, I guess, as they say. Yeah. Hey, Rex, again. I guess let's get into it. So last time we worked on chapter 8, we ended on number 2. Sounds good, Slim. Thanks for the raid. I appreciate it. So I guess let's get into number 3. The Excel draw should be posted.
Okay.
Okay, 3-dimensional spacetime has the line element.
Ooh.
Like that. Find the explicit Lagrangian for the variational principle for geodesics. Okay, that doesn't seem too bad, but I'll wait for you to get in.
I think I'm in. I was charging the pen, and I think I got the pencil charged up here.
I don't see you in it yet.
Let me see if I can do something. It's a little slower.
I see you now.
Yeah.
Okay. So I think finding the Lagrangian is just like figuring out what L is as a function. So I don't think that's the worst thing in the world.
How do we get L? We got the coefficients of the metric.
Yeah, like we set up that integral. Like S equals integral ds equals integral. Well, I guess we're doing tau, right?
Yeah.
Time time has 3 dimensions. I haven't heard that. You probably could make a line element that looks like that, though. Square root.
Actually, I got a question.
Mm-hmm.
Or maybe more of just a comment or a thought, because I was reading in another book this week about space-time, right? So you got 3 dimensions for space, and then you add the 4th dimension to get space-time, like we've been using,
Yeah.
to get like a 4 vector. And then they were saying, what did they say earlier in this book? They did say like, then you rescale the time by dividing by the speed of light so that you convert it to a distance.
Mm-hmm.
So in other words, the time is also kind of measuring the same thing as distance.
Yeah.
So, yeah.
It.
Okay. I guess that's all I was thinking about. And then there was the no, not the Minkowski. What was it? The Lorentz transformation. And you can, yeah, because we know how to make transformations in 3-dimensional space, right? Like you can rotate your axes or something, or you can translate it. But then when you got 4 dimensions, you can do some kind of 4-dimensional transformation, and it's like the time axis turns into one of the length axes, and the length axis turns into the time axis. It's crazy.
Was that the
So maybe I'm
hyperbolic
wrong about
rotation thing, or?
yeah, something like that.
Because like I've been thinking about that too, where like coming into this, like it's probably a thing to have heard that like, oh, in general relativity, time looks just like a dimension of space.
Yeah.
But it's still it doesn't seem quite that simple to me because I've noticed the time component always has a negative in front of it, and the others always have the opposite sign. So it doesn't seem the exact same thing as space, but it does look a lot like space. But it's still different in some way.
Yeah, it's got that negative sign.
Yeah.
All right, let me see what you did
I
here.
didn't flip the signs. So all I did was plug in the meaning of d tau. I got lazy, but this is where the book would do a second step of parameterizing it in sigma and like dividing it through and having a d sigma on the outside.
Right.
So I'm doing that in my head here, but I'm just kind of skipping straight to the Lagrangian part, which is the piece inside the integral, not including the integral sign itself and the d sigma.
Yeah. I got you. Oh, we got lots of R's here.
Yeah. Okay. So I think that's our Lagrangian. That seems for part A. Using the results of A, write out the components of the geodesic equation by computing them from the Lagrangian. In the geodesic equation...
I think you lost a -1 up here.
Ooh, I did. That -1 is really sneaky. I almost forgot it the first time. I don't have my snipping tool.
Okay, so the full disclosure is I haven't really looked at the book since last Saturday.
Same here. I've been full on with the complex analysis.
All right. So I'm not the only guilty one.
So I found
I
the
think it's gonna come back to me.
yeah, same. Um, I found the geodesic equation, but we needed to find the Christoffel symbols. Um, read off the non-zero. I mean, B and C seem kind of like, don't we have to complete C to do B?
Um, I was thinking we could do B and then get C. Because last
Uh,
week how did we do this last week? We did
we
because now we got to do partial DL D whatever, right?
yeah, we got to plug them into the Lagrange equation.
Yeah.
I need to get that again. I always forget. It's chapter 4, I think. Towards
Yeah.
the end.
Yeah, page. Where is it here? Oh no, chapter 5, I think.
Ah. Oh, yeah, it was in like 2 chapters.
It's page 90.
Page 90. Okay.
Yeah, it's in 2 chapters, but in page 90, it's a little more similar to what they're doing in this chapter
True. Yeah.
because they have the notation with the crazy exponents and stuff.
Yeah. And
I think it's
so,
558, right? That's kind of what we need.
yes, that's yeah. I
Yeah,
got
that's
it.
the one.
And so we basically used the Lagrange equation and then compared it with 8.14. Or I mean, no, these just give you the geodesic equations. We don't necessarily even. Oh, okay, yeah, I see. We only need 8.14 for part C. Computing or using Lagrange's equation will get us everything we need for part B, I think.
Yeah, this feels like the order we were doing it last week too.
I think so, yeah. Okay, so if we compute it, I guess for time, there's no t's anywhere here. We only have a dt in the first bit. So we get the 1 over 2L. And then we're going to do times 2. Ooh, we need the coefficient. Okay, times 2, 1 minus 2m over r dt d sigma. And we're going to need to remember that relationship between L and, or like, d sigma is equal to dl ds or something like that. But we can do that in a second.
Yeah, something like that.
And this just equals 0. Making sure I have this right. Hey, color cone, thank you.
Boy, Excalibur doesn't like me.
What's it doing this time?
You know, it just doesn't like to let me write more than one thing like per second or something. If I try and write quickly, it just stops writing. It
Oh,
doesn't seem to do that for you, does it?
no. Like once we've been using one for a while, it'll start to ignore my movements. Like if I try to do like a squiggle, it'll kind of straighten it out. But that's usually what I run into, not the other thing.
Yeah, I've noticed it doing that too, but it's got this other thing with me where it doesn't like to let me write very quickly. It's like, slow down there.
Yeah, slow your roll.
Yeah, slow your roll.
Okay, for this next piece, I think we do need or whatever that relationship is.
I think it's d tau equals L d sigma.
Yeah. And we sometimes have to do a trick with dividing each side by L or something.
Yeah.
Let me shove this out of the way for now. We'll bring it back later. Okay, so on the inside, let's deal with that first. The
Because what do we
twos
want? We
cancel.
want these things in terms of tau, right? I
Yeah.
think we want all our derivatives to end up just in terms of tau, I think.
Yeah, because that's how
Okay.
we want to parameterize our geodesics. Or that's like the
Yeah.
most natural choice. And then this d sigma on the outside, we can divide by L to convert it to tau. We can divide out the negative sign also.
Okay.
Now,
Yeah, this is definitely coming back to me now.
same. We do, I think this
Because
is a
this is where I
product rule on
got
the
stuck.
inside,
Okay.
unfortunately, because of R.
Oh yeah, okay.
So
So we're
taking,
not going to get a diagonal matrix this time. We're going to get some off diagonal things.
oh yeah, yeah. Okay, so derivative of that piece first, we'll get,
What's this M? That's just a constant, right?
I think so.
It's probably the mass of a planet or something, right?
Yeah, that's usually what the big M is.
Okay. Cool. Yeah, because that looks like some kind of a potential, right? M over R. Isn't that some kind of gravitational
Ooh,
thing?
yeah. The constant, I guess I don't know what's up with the 2 and the lack of the G, but M over R definitely looks like a potential of some kind.
Yeah.
Okay, and then we subtract that thing over and divide out.
Is it Minecraft's birthday today?
uh, I don't think so. I think you can have a Minecraft birthday apparently, according to Color Cone. I don't know
Oh.
what that would be though. Surely this can simplify so it doesn't look so annoying. Hey, Socknail.
Oh, I think, wait a second now. I think we need this DTD. We need this guy to show up here too, don't we?
Oh, I forgot. Yeah, I dropped that. I was wondering. It looked a little bit off. Oh, that's it. Yeah, that a year in Minecraft is 5 days in real life. It's like dog years. Okay, so I guess we can bring this thing in the denominator with the r squared. Minus 2m over r squared minus 2 mr dr d tau dt d tau. That doesn't look like much to me. And it doesn't necessarily have to. This is the time component. So I don't have much of an expectation for what it should look like, but... Oh, you know what? We have the 2 to fix that symmetry thing, because this is not a symmetric thing. That's probably the exact reason why the 2 is there.
Oh, maybe.
Because the actual Christoffel symbol we would remove that too.
Okay.
Okay, so I think it's our time component.
We got 3 variables, so
Yeah, I guess let's go for R next.
the fun one.
Oh god, the terrible
And
one.
there's all kinds of R's everywhere.
Okay. Gotta plow through it. At least the DRD sigma component will be easier. Okay, I'm gonna drop that exponent of -1. It's gonna keep messing me up. And times 2 drd sigma. Levi-Civita connection. That sounds familiar. We haven't learned it by that name, but I think that is relevant. Okay, then we do plus the partial with respect to R. Ugh.
Yeah.
Okay, so the easy bit, 1 over 2L. When in doubt, just stick a 1 over 2L on it. 2m over r squared. dt d sigma squared. It's the first piece. Then we have that piece. So we're going to get now plus 1 minus 2m over r to the negative 2. Chain rule. Times 2m over r squared. Because there's already a negative in front. Times dr d sigma squared. And then the last bit, minus 2r d phi d sigma. Equals 0. Oh my god.
Wow.
I hope we're going to get something cool from this geodesic. Like an orbit or something I'd be happy with. Hey, Phobos.
We could cancel the 2's.
Yep. Self-sums are the coefficient of that connection. Geometrically, it corresponds to the differentiation of vector fields, allows one to define acceleration in the geodesic equation can be interpreted as path with no acceleration. Okay. Dessen linked a video last time about Christoffel symbols, and I couldn't follow a lot of it.
I didn't watch it. Did you watch it?
I only watched the first part because they talk a lot about math that I've just never learned. But there was an interesting explanation in the beginning where they kind of say what Christoffel symbols intuitively mean. And they basically tell you how your basis vectors change when you travel an infinitesimal distance in each of your like basis vector directions. So yeah, they had a little like visualization with like a stick figure dude traveling along like an arbitrary coordinate system, and it was a pretty neat way of showing it. They talked a lot of manifolds and stuff like that I couldn't follow.
Also, hey Phobos and hey Drumcat.
Yeah. Have to greet Drumcat specifically. It's mandatory. Okay, so
You know what that makes me think of is the very last section of this chapter, where they were trying to talk about the coordinates, and they showed that little picture on page 180. Don't bother looking at it now.
Okay.
But I wonder if that has something to do with the Christoffel symbols. Who knows?
Probably. Why is... Oh, yeah, okay. Okay, I was questioning why this was 1 over that, but that's because I was looking at the wrong piece for where that equation came from. Okay, so then that's good for the first bit. For the second bit... Oh, yes, I'm going to divide by 1 over L.
I thought Drumcat was just named Drumcat because he was drumming his paws on the table. Yeah. But now I'm wondering if he's actually like, part of a metal band or something.
I mean, that'd be kind of sick.
All right, sorry. I got to get my head in the game today. I'm sort of All right, I'm here.
Less drum cap, more
I'm checking what.
geodesics.
I know. I know.
Minus r d phi d tau squared equals 0. Okay. So I divided each side by L. And then convert everything to tau.
Oh, you cancel the L's as well. Okay. Cross the L's out.
Well, I divided this L converted the DRD sigma.
Oh, sorry. You
And
didn't.
then
Yeah. Okay.
on the
I gotcha.
outside, I divided each side by
On the
L to
outside, you
convert
divided
that.
by L. Yeah.
And then we need the L squared to go in the squares here.
Gotcha. Okay. Okay. That was where I was getting screwed up last week, and you explained that to me. All right.
Yeah, yeah.
Okay.
And now we just isolate. Oh, wait, no, we need to do the product rule on the left side, and then we can bring it home. Okay. So we have a minus sign on the outside. Taking the derivative of that piece, we're going to get another minus sign.
You know, this is the same exact product rule. Oh, no, it's not because it's upside down.
Yeah.
It's flipped over. Okay.
That's going to be DRD tau squared because of the chain rule. 2m over r. Squared. Okay. Oh wait, other piece of the product rule. Minus 1 over 2, 1 over 1 minus 2m over r.
Is this squared supposed to be here?
Yes, because we had an existing DRDT, and then when we took the derivative of that r in there, we got a second one.
Oh, yes, thank you. Okay, I got it.
And that makes sense because we should always have two first derivatives multiplied for all of these things. So I think it's a good sign.
Oh, that's a good way of thinking about it too. Yep, I like it.
Important thing is those depend on the choice of metric. So concepts like acceleration are metric dependent. That's why when you try to compute the acceleration of a curve in polar coordinates with the usual form, you get the wrong answer. Ooh, interesting. Drumcat can do a modular arithmetic and modulate the syncopation, whatever that means. Okay. And then on the right side, that can all stay the same. We don't have to do anything with that in this step. Okay, now we want to isolate the 1 second derivative that we have.
Did you catch this term?
I sure didn't.
It's hard to believe this equation could be one term longer, but it is.
Yeah, there just aren't enough terms here. Let's add some more on. Good catch, though. Actually, we could subtract these over in this step. Maybe we should do that. We'll take a positive one of these, then a negative of the others. I mean, we're about to flip the signs right back, I guess, but flip that, flip that. Okay, does this... am I still dropping the D? No, okay, I did get the DT detail.
I think it looks good.
Yeah. I do still prefer pen and paper, but anything electronic is really nice for stuff like this.
Yeah.
And you really have to move symbols around. So we're going to subtract over the final term we didn't get to. Copy all of that. Then stick on a minus with that. Okay, final step, multiply through by negative 1 minus 2m over r. So it's kind of interesting that only phi is negative. Or like the dphi dtau is the only negative we get out of this.
Mm.
I guess it comes from a difference in, it has a positive r squared. Like the exponent is positive, whereas there's negative exponents for dr d sigma. So negative 1 minus 2m over r. R minus 2m d phi d tau squared plus, hey Shoria, I don't know if there's a real point in multiplying the m over r squared in. From 2023. Oh, hell yeah. Thank you. So G.
And these ones, you can just reduce this exponent, right?
True. Yeah.
Uh-oh. Am I here?
Yeah, you're here. Sorry, I said true. I hope that came through.
That happened last week too. I heard my Discord. I heard myself drop out and come back into the chat somehow.
Huh. Sometimes
Not sure
Discord
what
is weird with stuff like that. Did I drop exponents? Maybe I just didn't copy paste them right on the first derivatives. Those should be squared though. Oh, we have two DRD tells. Wait. Does that make sense? Hey, Dram.
Yeah, you're right. I just noticed that. Oh, they're like terms. I'll be damned. This over here and this over here were like terms.
Yeah.
They don't cancel, do they? That'd be lovely.
One of them has a 2, the other doesn't, it looks like.
It looks like that's just going to become a...
Oh, I guess it makes sense if we get 2 of them.
Yeah, I think it makes sense.
So they have the same sign. So we're going to get a 3m over r squared?
Yeah, looks like it.
Interesting. There's no mixed derivatives here.
Yeah, that's weird, isn't it? Oh, I guess not, because I would have expected it was going to come from here, but this is just already has taus and r's in it, and that's all it has. So, yeah, okay.
We only had a function of r for the for like our coefficients, so there's an opportunity to get another one, I guess. Okay.
All right. Then phi. Phi is going to be the easiest one, I think.
Yeah, or at least about the same as t. Okay, so God, this is so much writing. Minus d sigma 1 over 2l so this is d phi d sigma, or dl d phi d phi. Dude, this notation sucks, but I also can't suggest a better one. Okay, so it's going to be minus 2r squared d phi d sigma. Equals 0. Okay. Yeah. You're the two canceller.
The mysterious two canceller. Striking from the shadows.
Yeah. Convert it to d tau. Hope you're doing well today, Dream. 2r dr d tau d phi d tau plus r squared equals 0. So d squared phi d tau squared is minus 2 over r dr d tau d phi d tau.
That's part B, isn't it? I think that's it.
Yeah. Assuming we didn't make some small mistake on the way there, but yeah.
Now I have another question. Why is this Lagrange? Why is this metric only got 3 variables? Does that just basically mean that in the other like the z-axis, it's just nothing's going on?
I guess so, yeah, like it's just a constant z equals 0.
Okay.
A two-dimensional space that's changing in time, I guess.
Cool.
Okay, so theoretically,
I
C
should be happy.
quicker.
It's always nice to have one less dimension to work with, I guess.
Yeah, after the journey we went through to get it for R, I don't want another dimension.
Yeah.
I hope this is. I feel like for whatever reason, this could be like an orbit of some kind. We're looking at it only in 2 dimensions. I mean, it looks like we have some kind of gravitational potential.
Yeah. That's what I'm thinking, maybe. Okay. Oh, wait a second. Doesn't this look like that thing from chapter 6? What was that called? Static weak field metric.
Ooh, a little bit. I think they're using phi instead.
Yeah, but that's what I'm saying. Our phi could be this 1 minus 2m over r.
Yeah.
That might somehow be like a potential function or something.
I mean, that's basically what phi is, yeah. Found it. Oh my, yeah, it looks almost the exact same. I guess one of them is inverse. They gave it in Cartesian as well. There definitely is a big similarity, though. It's page 126.
Yeah, it's Cartesian instead of spherical. I mean, maybe it's got something to do with that.
Because we definitely have a 2 phi and like a 1 minus. I guess we only have 1 minuses, but. Read off the non-zero Christoffel symbols for this metric from your results in B. Okay. So then for gamma time, we have an RT equals TR. Okay, so the negative sign is built into the equation, so we take away the negative sign that we got there, I think.
Yeah.
And we divide it by 2 because it's an off diagonal. Okay. And then, okay, for R, we're going to have 3 different ones, all of them like doubled. So we have, I guess we'll do TT first. M over, and we insert a negative sign. Minus M over R squared. Actually, let's just copy paste this. Okay. And then phi sub R, or sigma, then we have phi. We don't divide by 2. Yeah.
That's your sigma, that one.
Oh, thank you. Or phi.
Up to phi, yeah. Sorry, phi. I gotta start doing Greek letter flashcards because I always screw them up.
I I get those two mixed up a lot also. Oh, wait, why did I insert the negative sign? That one we don't want a negative sign. Wait, do we?
I don't think so. You're right. If it's negative, you flip it. If it's negative,
Right.
it's positive. It's positive, it's negative. Yeah.
Okay.
You just flip it, I guess. Yeah.
I'm sorry to hear that suck now. I hope it went well. I'm super zoomed out. Let me get the negative sign. There we go. That's what we get for R. For phi, we just get an R phi. So we have a minus 2 over R, so it's going to be positive 1 over R. Okay. That's some... I feel like I did a physical exertion there. Like...
Yeah, nice work. Nice work. Now, what if we were thinking about, for example... Yeah, I'm just getting a little confused because I thought because we had 3 letters, I was trying to think of it as a 3 by 3 matrix, but it's more than that, isn't it?
I think it's a couple of matrices.
Is it 3 by 3 matrices? Is that kind of what we're working with?
I think so, yeah.
Okay, it's 3 by 3 matrices. Okay. And so this last one you got, does that mean if you're doing the matrix for phi, there's only like 2 non-zero elements in it?
I guess so.
So the diagonal of that one would be zeros? It'd be interesting to try and understand what these things mean, huh? Like you said,
Yeah,
if they're telling us something about mass and distance or something.
Yeah. We figured out the matrix representation the last time, right? What was that? I'm bringing up our notes from last time. Okay, yeah, I think it's a separate matrix for each coordinate, like we said, because we did the kind of like in other contexts in linear algebra, you have like xy times a 2 by 2 times xy. We were doing that, but with like derivatives, and it worked out. So yeah, I think we have 3 by 3 matrices.
Okay.
And I think you're right that they'd be pretty sparse.
Yeah.
Like the one for R is diagonal. The ones for time and phi both only have 2 non-zero entries. The coefficient you obtain is your differentiate with respect to your coordinate vector fields. These are the derivative of vector fields. Okay.
Yeah, I got to watch that video you were talking about of the Christoffel symbols. I still got it open on a tab here. I just saw it today, and I was like, I didn't watch that.
Yeah, I mean, they seem to go pretty deep into it, but it was cool to watch it for a bit at least. Okay, next one I grabbed is number 7. Where should I bring it? Maybe I'll just bring it down below. Okay, consider a particle of mass m moving in a central potential v of r in non-relativistic Newtonian mechanics. Write down the Lagrangian for the system in polar coordinates. Using the method of section 8.2, show that invariance under rotation of the z-axis implies conservation of the z component of the angular momentum.
Wow.
Okay, so I think we have to go back to the definition of Lagrangian when they first introduced it, where it's either k minus v or v minus k.
Yeah.
Where did they first introduce it? Was it in... it should be in chapter 3.
Yeah, the first time they
Yeah.
brought it in was the very end of chapter 3.
So 1/2 m velocity squared minus
Potential.
potential.
Write down the Lagrangian in polar coordinates.
Yeah, I don't quite know how to express the velocity in polar coordinates.
Can we just assume that this is going to be in a plane instead of in three dimensions, 3 spatial dimensions? Okay.
Because we're rotating about the z-axis, but that's just a regular rotation. I don't think we need to worry about three dimensions.
I think the velocity is, I think the dv is dr plus r d theta.
That sounds right.
Or I should say dv squared is dr squared plus r squared d theta squared, I think. I don't know if I said that right. No, that's not dv, that's ds. That's ds, isn't it? That's the...
Yes.
Yeah, because if you got polar coordinates, the ds squared is dr squared plus r squared d theta squared. Let me write it down and see if it makes sense. ds squared equals... Oh, and then to get velocity, you just divide everything by dt squared, don't you? That should work.
I think so. Yeah, that feels right. Terrible question. Equation.
Yeah, okay, cool. That looks good.
Yeah, Dream, that's kind of the issue with using ChatGPT for things. Like, if you don't know how to do the problem for yourself, you can't really verify easily that it's actually right. I don't, it kind of, if there's a website to check if something works, it kind of depends on the field. If it's simple enough, Wolfram Alpha can do it. Also, Jed, thank you for the streak. It's to do actual like computations with. But it's kind of hard to answer that question in general. Dirty 30. Using the method of, okay, what's section 8.2?
Oh, 8.2. That's where they were doing the killing vectors.
Oh, crap. I should have chosen a different one.
Maybe we can work out what the killing vector would be. Oh, yeah, look, 829 there. That looks kind of like where we're at. Equation 8.2.29.
Yeah.
Oh, except that's 3D. We don't even need that third term.
Mm-hmm.
Yeah, we were talking about this last week.
Maybe example 8.7 is the closest one that we have, because here they find that geodesics and polar coordinates are straight lines. So we're working with the same polar coordinate thing. They say the killing vector, the metric is independent of phi, or we're using theta, I guess, but who cares? The killing vector has r component 0, phi component 1.
So our Lagrangian depends on r and theta.
Well, it depends just on r. The theta is the derivative, right?
Oh, yeah. So it doesn't depend on theta. It depends on how quickly theta is changing, but it doesn't depend on theta per se.
Yeah.
Right. That kind of makes sense, right? Yeah, because we know that this potential is one-dimensional. It only matters how far it is from us and not what angle it's at. And the same thing with the velocity.
I think so.
Is this last one d theta ds squared?
It
Wait a
is.
second now.
Yeah. Thank you. Because the t that we use in the Lagrangian is just a generic parameter.
How did this killing vector thing work again? Once you got a killing vector, there's a way to find a preserved quantity.
It's Kasai dot
And somebody
u.
in chat was explaining it last time, or actually it was somebody in physics and depressions chat was telling me about it later that day.
Oh, okay.
Yeah, it has to do with the velocity, the dot product of the velocity and the killing vector is a constant, and whatever that constant is, it's some kind of conserved quantity of the system. So I guess in this case, it's going to be angular momentum about the z-axis that's going to be conserved. Oh, God. Yeah, here's where my basic mechanics fails me. I don't even remember the units for angular momentum.
Me neither.
It's like, isn't it? It's the
Wouldn't it
like
just
moment of the
mass
moment.
or something?
I think it's linear momentum times a distance, isn't it? It's like a torque of a linear momentum about an axis. So I think it's a mass times a velocity times a distance.
Kg m squared inverse s.
Okay.
It's equal to I times omega or r cross p.
Yeah, that's what I was thinking of. R cross P. It's like a momentum times a distance.
Don does Riemannian
Okay,
geometry. Tries to. This is one of the few chapters I didn't get to in the mechanics book. So I'm really rough on angular momentum.
Yeah, me too. Me too.
So we know that
I'm pretty good with physics up until things to start turning around. You know, as long as they're just like point particles moving straight, I can do things really well.
okay.
Even uniform circular motion, I finally got my head around, but angular momentum, I never really did.
Okay, so the definition of Kasai I just stole from the example. U, I hope it's fine to just say that U is drdt, comma r d theta dt. We're going to need to find the outward relationship between t and s, I guess.
Is this right here r and theta?
Yes.
I'm wondering if we need a third. No, we shouldn't, right? That should be good.
I think so.
Okay.
And
Well, then if we dot product these, can we do that?
yeah.
Oh my God, is this going to work?
We have to care about the coefficients of the metric because the dot product.
Oh, yes. Yeah, that's right. Didn't we learn that the hard way last
Yes.
week or the week before? Maybe it was the week before. We got yeah. So that was the chapter 7 thing, wasn't it?
Yeah.
Okay. So
it's GAB Kasai AUB. So
we got 1/2 m on the first one and 1/2 mr squared on the second one. I think we need the mr squared, don't we?
wait, that's the Lagrangian. The G's are from the metric, right?
Okay. So okay, good.
Okay,
So we need the r squared.
yeah, we would have a 0 drdt times a 1. We have no mixed differentials, so the 0 times r d theta dt gets multiplied by another 0, and the 1 times tr dt gets multiplied by a 0. I think we only care about the 1 times the r d theta dt times the r squared.
Okay.
But I don't like r cubed.
No, I don't either. I wanted r squared. Are we supposed to take the square root of these things?
Uh, Yeah, how is G defined again?
Yeah, it might be like the square root.
No, I don't think it is the square root. I'm looking at page 138. It's not G squared in the definition of a metric.
Okay.
But I agree, our cubed is probably bad. I think there's something wrong.
It just doesn't feel right. I feel like we want r squared here. Well, let's think about angular momentum. We said it was going to be a moment. It was going to be a mass times a velocity times a distance. Yeah, what about m? Where's m show up in all our equations here?
I think we can equivalently consider Kasai dot P. I don't know if Megalomorph, we have gotten to Christ awful symbols. Yes, we just have learned about those in this chapter. So we could also say that Kasai dot P is conserved. But there's definitely something wrong. How do they get this here? Right now we're getting killed by killing vectors. But we were just doing Christ awful symbols. The components of the tangent vector u are just dx, dA, ds? I wrote down u wrong, I think.
You did? Which part of it do you think's wrong?
The r. And apparently also the t.
Where do they come? Where do these things come from?
I thought I was just saying the general definition of velocity, but the book is saying that it's just the derivatives. Maybe because doing it in... I wonder if converting from t to s would have solved this? I wonder if the r disappears somehow. If we're parameterizing s. How do they figured out by integrating it, the relation between s and the parameter.
So r squared d phi ds. Well, that's basically kind of what we have now.
Yeah, that
I'm
would...
looking on that 8.7 example.
Yeah, I think that would fix things.
Now, first integrals. First integrals.
Shouldn't the Lagrangian and the metric match up better?
Well, there's like two ways of doing it. There's the way you're doing it on the left, and then there's the other way from chapter 3 where they were using that potential, right? Like kinetic energy and potential energy.
But yeah,
There
you're right.
must
But
be
like, what
two
did
different
happen to
ways
that
to,
mass though?
yeah.
Like, we should be able to get the same thing.
Yeah, I would think so. Is ds dt the same as velocity?
I thought so. I think so.
Could we say this d theta ds here? Could we say like d theta ds is d theta dt over ds dt, which is omega over v, which is 1 over r maybe. Is that right? But I don't want it to be 1 over r. I don't think that's right. I don't think that's right.
Okay. I know. I feel like there's a disagreement between the Lagrangian and the metric. I don't. I don't know how to fix it.
Did they do a Lagrangian and polar in this book? They probably did somewhere by now.
I don't remember. They probably did it towards the beginning of chapter 8, right? Like, we could just take the Lagrangian
Oh
that we
yeah,
wrote.
8.1. 8.1.
Right.
That's kind of what we're doing a little bit.
I did forget a square root on the outside. No, I didn't. Well, how is that equal to k minus v? I
Where's the k minus v?
or I'm looking at equation 8.4. That doesn't look like a kinetic energy minus a potential energy.
Oh,
How the hell? What the hell is a Lagrangian? I feel more lost than ever. Like, they defined it two different ways, didn't they? Now,
are there any physicists in the chat?
like, that's how we were introduced to the Lagrangian as kinetic energy minus potential energy, and that we're not. We since then we've been getting it some other way with like looking at the world line, and it doesn't look anything like.
Yeah, okay. What about this? Yeah, what about that equation 8.1? Is there any way we can see how to make that Lagrangian look like, k minus kinetic minus potential? Oh, maybe that whole thing. Oh, you know what, Don? That whole thing is just kinetic energy right there. That is kinetic energy. That's what we were talking about. It's like dr dt squared plus r squared d theta dt squared, and then square root. So that's just the kinetic energy. So there is no potential for this 8.1 function.
Isn't it just
problem.
velocity though? Like there's
Yeah.
no
Oh,
one
yeah.
half
Well,
m?
there's no 1/2 m, right? But didn't they? You just read in that other question where they said you could use you could use momentum instead of velocity or something. So maybe it's because masses can. Maybe we don't have to worry about the mass because mass is constant. So maybe we can throw out the 1/2 m if we're just doing a problem with no potential in it.
Maybe.
Maybe.
I learned a differential geometry class went way beyond its scope. Yeah, no worries, Mega. Like, we could just take the Lagrangian that we've written and just blindly apply Lagrange's equation, or Lagrange-Euler equation.
Yeah,
I don't know.
we can, right? Let's try it. But why don't we try it? And I don't know what's going to happen to the V.
Yeah, I wonder if the reason we haven't had a potential is that we've been like, this should be accelerated if it's moving in a potential. So maybe that's why it looks different now. We've always been talking about free particles with no accelerations.
Yeah.
This could be the beginning of a change of focus. Next is Don does Nat Geo, then Don does GeoGuessr. GeoGuessr would be a lot easier than this, let me tell you. Okay, so minus D, I guess why I'm using T. We could also use sigma. I want to use sigma. I'm too used to using sigma now.
Yeah. I like sigma.
Even though they come out looking like sixes half the time. Hey, Ved. Okay, this one is for R. So we only have one DRD sigma. One half M times 2 dr d sigma plus.
Oh, except you know what now? Because we got this extra VR over here, then it's not 1/L anymore, is it?
Oh.
We could change this to L plus V down here, maybe. That might be an easier way to just deal with it.
I was wondering if that actually is L
Except
plus
then
V.
we got that V tied up in here.
What did they do with they plugged it into the Lagrange equation with the V, I thought. Did they not? Wait, mx double dot, like kinetic, or well, I guess it's. Wait, so potential energy is hidden inside the Lagrange equation? I'm looking back at chapter 3.
Yeah.
Okay. This is page 43. I'm looking at just above 3.34. So a force is a negative derivative of potential. Huh. Am I? Are we worrying? Like, should we not have the V of R explicitly out here? I I feel like the book does somehow start with k minus V, but they do change into just a normal Lagrange equation for reasons I'm not completely clear on now. I think I understood it at the time. Yeah, but that's right about the Lagrangian.
I think you're right that for the better part of the book so far, they've been working with free particles, right? And what does that mean? If it's a free particle, the potential was zero. Is that what it means? No, it doesn't feel like that would have to mean it was zero.
No, I think this already considers having a potential energy built in. That's what it feels like. I don't really know how it's represented in the way that we're doing it. Hmm. Non-relativistic Newtonian mechanics. In ugh.
Okay, what about page 129? Page 129, like right at the end of chapter 6, where they were doing that static weak field metric. And I'm just looking at equation 628.
Okay.
What does that say? If multiplied by the mass, 628 is just the Lagrangian for a non-relativistic particle moving in a gravitational potential phi. Isn't that what we got?
I guess so, yeah.
Where did that phi come from? So that phi is the same phi that was showing up in that metric. That static weak field metric, that phi function.
True. Yeah. Ved, I do know about Gauss's law, but uh, right now we're just talking about general relativity. If you want, I can talk about that in like 45 minutes or so. Phi showing up out of nowhere reminds me of my cable company.
Yeah, I don't know if this helps us. It seems related.
Okay, maybe this is one where we look at the first sentence of the answer. Or like just the first like
Yeah,
bit.
yeah, why not? Oh, he put an S on it too. He curses us with these S problems.
Yes.
He's probably gonna write down. It's probably gonna be like a 2-line answer.
It might be. I'll have to be careful with how I scroll.
Oh, by the way, we didn't look at the answer to the one before
Oh,
this. If you want,
yeah. What number? It's 3?
3, yeah.
Oh, this is... Oh, no, not the dots.
Oh, they're writing it in terms of dots. I actually kind of like the dots.
I don't... It's really not clear to me there, but... Like, the dots are easy for me to miss. Part A... I mean, part A was pretty simple. We got that right.
Okay.
Part
So part
B...
B, we had like 3 different equations.
Oh, lazy. They didn't go all the way through with it.
Oh,
Or like they
oh, they
never
left
did the
it without
product
doing.
rule.
Okay.
But we can verify at least that step. d tau 1 minus 2m over r dt d tau. Okay, the t part matches.
Okay.
The r is going to be annoying to verify, but
Yeah, I know.
okay, wait. Let's do the
They
phi
wrote it.
first. Stateless phi. d tau r squared d phi d tau. Okay. And then that line right there. d tau.
Maybe they did do a little work on the R1 because they got 2 lines at the bottom there.
Yeah, they still don't do the product rule, but R just has so many terms
Okay.
they couldn't compress it that much.
I mean, it looks right to me. Just looking at it quickly.
Uh,
Yeah, they
I'm
only
saying
went to
we
like
dropped a minus
your second
sign.
line. Really?
I think we needed a minus sign here somehow.
No, come on.
But they had a minus sign outside and a minus sign inside.
Hmm. Well, why is that?
So this is for the dr sigma derivative. There was a minus sign on the outside. The negative one comes down to make it positive. I don't see where the minus sign comes from. It seems positive on the inside.
Let's see what they said for Christoffel symbols, because
We got the entire rest of the equation right, just that one little negative sign. So we should just be off by a sign, I think, if
weird.
anything. Unless that made us get a cancellation for the DRD tau. Okay, that term would be the telling one. Oops. Christoffel symbols. Okay, gamma t 1 minus... Oh, I kind of multiplied things out. I think these are equivalent. Yeah. Are they?
Well, at least the 1 over R looks good.
Yeah, okay, yeah, these are equivalent. The 1 over R, yeah.
R minus 2, I'm missing the negative sign. Yeah, maybe there is a negative missing. Oh, well, that's fine. I mean, we got the... Procedurally, it's good.
Yeah,
I think I do see I think I see a negative missing here, maybe.
Okay, because I can't find it.
What about in the first line here, like here? Isn't there... Because you move this to the bottom, but isn't there still this negative here? Would be like here somewhere?
So...
Yeah, this one.
Oh...
Is it or isn't it?
Wait. Yeah, I think I accidentally started to take a derivative and I put the negative 1 out front, maybe. But that's not the thing we're taking the derivative of in that stage. So I think you're right. That negative sign out front should have stayed.
Oh, well, too many negatives.
um,
They didn't
Fairmon, hey
explain
SP.
anything about what these symbols were standing for, did they?
The Christoffel symbols?
Yeah,
Or...
like you said about having some kind of orbit. I was hoping we'd get some kind of explanation.
Oh, yeah, I agree. I wish they said that. Maybe it'll come up in a future chapter or something.
Yeah.
Um,
Or maybe it's just made up.
maybe.
It could be.
I'm being maybe a little bit too extra, and I'm actually going through and fixing these signs. That should have messed up all our signs.
Really?
Yeah, because I just flipped that second derivative one from minus to plus.
Yeah, it should change both of these because there was two terms then, right? Like both of these.
Wait, should this one stay as negative? So those two negatives cancel. We get a negative one out front from the outside derivative, then from the inside derivative. Okay, yeah, there should be negative out front. So that negative goes away. The drd tau squared becomes a plus. And so...
Maybe we won't get a 3 anymore.
2m. No, I think we get just a +1. So you have a -1 and then a +2. And does that match with the Christoffel symbol?
Yeah, they don't have any 3s in theirs, do they?
Right, they don't. And I'm getting a positive in that equation, which means a negative for the symbol. Okay. Oops. Okay. Armand, I know this is basically a group study session. I'll do math help in 30 to 45 minutes. Okay. Okay, so we were looking at, we're going to peek at number 7, right?
Number 7, yeah.
Just want to know what Lagrangian is. Okay, so we had the right idea for what Lagrangian is. In polar coordinates, I'm going to peek at that part too. What?
Oh, they did go to 3D.
Why?
Well,
ugh. Okay.
Maybe they didn't want us to assume it was I just figured we could assume it was moving in a plane.
Yeah, that's what I thought too. Okay.
Actually, I read a book recently. Maybe it was this book. I forget which book, but it was saying that you could prove that if a particle's moving in a central force problem like this, where you just have like only one force, like attracting it towards the center at all times, then it has to move in a plane. It's planar motion. So you could just, change your coordinate system so that you rotate your coordinates so that you're in that plane, and then you are in a plane.
Oh, yeah, that would make sense. I really hate that they're switching theta and phi depending on how they feel in the moment.
Are they?
I swear this is the opposite convention than they normally do for theta and phi. This is the math convention, I think.
Yeah, because now the theta has a sign on it.
Oh my god. It's terrible.
Physicists.
Okay, so the
Well, we
Lagrangian is
peeked at the
definitely right.
problem answer, and then we just ended up making the problem harder.
Yeah. And I still don't know what we do with this Lagrangian now.
Yeah. Well, now we got something that perfectly matches that example in the book, because now we're in 3 dimensions.
Oh, back to 8.1?
8.7, wasn't it?
Oh, that one,
8.6.
yeah. Or
8.6. 8.6 says when polar coordinates are used, you have a killing vector
right.
because the metric is independent of phi, which corresponds to rotational symmetry about the z-axis. This killing vector has components 0, 0, 1.
Hate ND vines. Show that invariance under rotations about the z-axis. Invariance of what? I guess length?
Yeah, the ds squared, right?
Yes. But our ds squared definitely does not match our L as written.
Well, we could add the extra term in to the ds squared now, I guess, because they're going to have one of these showing up here as well.
Yeah, maybe. I just hope it's okay. I guess I'm worried about like the potential and the mass part of it, I guess. That's. I still don't know what to think about that, but. Pasty head? Hello? Your worry shall soon be dispelled. That's a reassuring fortune. So what's a rotation about the z-axis? Are we adding... Are we incrementing theta by some amount?
Yeah, I think that's all we're doing. We're just incrementing theta. Yeah, because if you rotate above the z-axis, then obviously z stays the same, but r should stay the same as well, right? If you're just rotating.
yeah.
Oh, and in this system, then phi would also stay the same, wouldn't it? But theta would be increased.
And so example 8.6 says the killing vector for rotational symmetry about the z-axis is 0, 0, 1. Like the phi component is the 1.
Yeah.
Um,
So should we try and do the velocity again like we did before? Is the velocity more complicated now? I guess we need a third dimension.
Yeah. Ooh, so are we d sigma? I think so.
Yeah.
I'm just taking the square root of everything blindly. Or wait, I said not to take the square root though, right? Dimensions wouldn't work out if it was squared though.
That looks good to me.
Okay, I don't know what looks good to me anymore, so I think it should be like this.
So if we had 0, 0, 1, we'd kind of get this along with whatever that thing from the G. What's the G called again? That's called the metric, isn't it?
Yeah.
Because I'm thinking of the DS as the metric, but that's not the metric. The DS is a line element.
GS is a lineup.
DS.
Oh, DS, yeah. That's like an infinitesimally short line.
Yeah.
What should we be like? So should we be expecting? Yeah, I guess we should be able to figure out what answer we expect at least, right? Like the second derivative of theta equals 0 or something like that.
There's a conserved quantity, right? So it's kind of like MVR, mass times velocity times radius, right?
Think so, yeah.
Um, yeah, how do we write it in terms of an angle? This is one of those Kepler's laws, right? Like when you have something orbiting, you have equal areas swept out in equal times or whatever.
Ooh.
So if here's the sun, and this thing's like going around it. And if this, is like 1 month or something, then maybe 1 month is also like from here to here, right? Like this would be, these areas should be the same if it's the same amount of time.
Oh, interesting. I haven't learned orbital mechanics, so.
And it's an ellipse, and this is one of the stars at one of the foci of the ellipse. And so r is the distance you are from the planet is from the sun. And then theta is, so I'm not really worried about phi here because I'm thinking phi is,
This is like planar
you know what?
motion. Phi should be a constant.
Yeah, well, that's the thing. I'm thinking of working in a plane again, but I don't know if we really are working in a plane.
I mean, we're rotating about the z-axis, so I feel like that's fair to say.
Yeah, I want to say the z-axis is coming normal to this plane, right?
Yeah.
Like
Mm-hmm.
But it could be that the z-axis is not normal to the plane. Like it could be if I tilt this sideways and look at it sideways, and here's my xy plane and here's my z-axis, right? It could be that there's the sun and that the planet's actually going like this, like this around it.
But we could always just
With
rotate our axes, right?
Well, yeah, I want to, but if we rotate the axes, doesn't that mean that we're setting phi equal to, what are we setting to 0? We're setting something to 0 here if we rotate the axes.
I assume that we would hold phi as a constant. So I guess that would mean d phi d sigma is 0. Like, there's just like no change in phi.
Oh, so maybe you're saying this could be my angle phi here, like the angle from the plane that the planet's moving into the xy plane in this side-on picture here.
It might be measured from the z-axis, but yeah.
Oh yeah, maybe up here. Okay, that's cool. Okay, so if phi was constant, then this third term in our line element would just be 0 anyway.
Yeah.
And this here would be 0 in our velocity because it's not changing.
True.
Okay, I like that. I like that. Okay, so let's say that's true. Let's say phi is constant.
Also, r is constant.
Well, no, I don't think r would be constant because it's not
It's
necessarily
orbiting.
a circle, right? Yeah. It's not necessarily in a circle. It's like it could be in an ellipse. So let's see. If I erase this and make this the xy plane here. If this is x and this is good enough, and this is y, then where's phi? Maybe, sorry, not phi. Where's theta? So theta could be like here, right? This is theta.
Yeah.
Okay. And so linear velocity is,
Hey, Young Lane, welcome in. Virtual particles and 0-point energy. That might be included in general relativity. I haven't heard those terms. If it is, we're not going to get that far, I think, though.
Yeah, I never heard of those.
Yeah, right now what we're doing is pretty, like, mathy, differential geometry-ish. The book we're using takes a pretty unconventional approach, it sounds like. And it's a pretty big emphasis on differential geometry, so we've been kind of struggling to just get through this math bit to actually get to the physics. Even then, the physics aren't very easy. I wonder if we're overthinking this.
Oh, yeah, I think so, considering it says it's an asked question.
Because, yeah, I...
Wish I could at least remember how they did angular momentum. It was r cross p, right? So r cross p, and p is mv, so that's mass r cross v, and r cross v gives me a vector in the up out of the plane, right, in the positive z direction. So okay, let's think about this. So it's mrv. It's not sine theta, is it? It's So here's R, and here's V. Oh, I don't know what the angle is. If it's an ellipse, then I know the formula is for when it's a circle, but I don't know how to work this out when it's an ellipse.
Hey, Alex here.
There is a quantity that is preserved that we could write in terms of R and M and theta, I think. I just don't know how to do it. And I don't remember what it is. I could get a physics book off the shelf.
No, I think that there should be something simple we can do here. Like, I think we should have to worry about a particular path a particle's taking, like an ellipse or something like that.
Yeah, I know. I'm trying to reverse engineer it. I know.
Okay,
I'm
okay.
sure we're not supposed to have to do that.
Oh, man.
Okay, well let's just go back to what you had here. So, and then can't we say that the killing vector, which I'm going to call K because I don't want to write that other craziness, is 0, 0, 1.
Yeah.
So then what do? We do a dot product of these two guys, but we have to take into account that G, which I never remember where to get the G from. So it's 0 times this, 0 times this, 1 times this, and we don't have any cross terms, right?
Yes, like the G here is 1 r squared sine squared.
Oh.
Like that.
Now, where did you get those? They come from the line element? No, they come from...
Yeah, the line element.
Yeah.
So it's like dr,
Oh,
d theta, d phi. Oops.
okay.
Dr, d theta. Yeah. But we're
And
going to get the same like r cubed
root.
issue if we do just this, though.
Yeah, we're going to get r cubed times sine squared theta, aren't we?
So I don't know what the deal with this is. Oh, I don't know why I wrote... That's just wrong. Should be like that for the line element. It's not a big deal, but...
Oh. We never did use the Euler-Lagrange equation this time, did we?
Well, that's what we tried to do, but then we got stuck with what we did with the V of R.
Yeah, what do you do with that V of R? Because I'm just looking back at example 8.1 again. And the bottom two equations on page 171 in example 8.1, it's when they came up with those two differential equations, right? Like the coupled differential second order differential equations, before they talked about Christoffel symbols and everything. And the second one has dds of r squared d phi ds equals 0. And so basically, it's when you look at it, you can say to yourself, oh, okay, then what's in the parentheses has to be a constant, right? So r squared d phi ds has to be a constant.
With respect to S, yeah.
Yeah, well, it's just...
I guess it's an ordinary derivative, so yeah.
Yeah, so So the square of the radius times d phi ds is some kind of constant. So what does that mean? If we think of s as time, right? Let's think of the s as time, I guess. So the radius squared times the angular velocity is 0. Yeah, didn't we talk about this before? So if your radius is smaller, you're moving quicker. That's another thing here. So that in this picture, that explains why, I don't even know if I did it well enough. I mean, it probably has to go up.
Oh, you sweep out more area.
Because you're moving more quickly in here. See, you're sort of moving more quickly.
Yeah.
And when you're further away, you're moving more slowly.
Okay.
Well, anyway, but I still don't know what to do with as far as
I think let's
showing it with formula. Yeah.
Go a little further down the solution.
Yeah.
Rotations about the z-axis are generated by phi sending to phi plus phi constant? Excuse me?
Oh, don't tell me I had the phi and the theta backwards.
This isn't right. That's not about the z-axis. No.
Because he got his symbols, his Greek letters mixed up.
Where the hell does... I just want the general... Freaking... spherical coordinate conversions. Actually, that's not the exact thing that I wanted. There's no way that theta is still the axis measured from the z. Where do they first do spherical coordinates?
Oh, that was chapter 2?
They
Yeah,
are
right
measuring
there.
theta from the z-axis in this image. But...
Yep. It might have been me, Don. I might be screwing it up. I probably
think I
was.
screwed it up. Oh, what the hell?
Yeah, the
Okay.
picture I drew
I guess they
doesn't
didn't
match with
reverse
your
it.
ds squared, does it? I think I screwed it up. I should have had phi in the plane and theta coming down from the z-axis.
That's so annoying.
Yeah, it's kind of annoying, but at the same time, I just don't understand why I can't wrap my head around it. It's so stupid. I mean, it should not be hard. I mean, I mean, it's frustrating that math and physics books have it reversed like that. It's just frustrating, but at the same time, it's like, you know, I should be able to sort it out. Good heavens! All right.
Yeah, same.
Okay, so this is theta, and this is phi. Okay, so that means we can treat theta as constant.
That would make more sense because if we made like the sign would get messed up if we made it theta plus a constant.
Yeah.
Young Lane, the arrow just means a regular old three-dimensional vector, yeah. We also have the 4-vector general relativity that we denote with like a squiggle underneath it. But we don't have those in this question.
Oh, you got some kind of linear algebra question there.
I can try ASP.
All right, so does that resolve us from our troubles here? Does that make sense then? So let me see if I understand what's this K. So this is still, so this is R. Ugh.
Niabo, thank you for the follow.
Okay, so this is R, this is theta, this is phi here.
Oh. I think,
Aren't
okay.
we still going to get R squared sine cubed theta? R cubed sine cubed theta. What?
I'm looking at equation 8.26, where they do a similar thing where they send x1 to x1 plus a constant. I think it's just Cartesian
Yeah.
coordinates. Is this... I feel like we can do the exact same thing, but with phi. Because if x1 gets sent to x1 plus a constant, dx1 would get sent to dx1.
Yeah.
But, and since there's no phis inside either the Lagrangian or the metric, I guess the metric. Well, that's not necessarily angular momentum in particular. Okay, never mind. We have some more work. Okay, never mind. I don't know how we get to angular momentum specifically.
What about this equation 831? I never wrapped my head around this. There was way too many things being set equal to each other.
No, I can never figure out every last one of these equal signs.
Because I think if we could understand all this, maybe that would help us know what we got to do next.
I think that probably is what they're about to do. We're just not
Yeah.
getting anything that seems meaningful.
I don't think I understand. You know what? I just don't understand the velocity vector. I don't know how to get this. What if we dot it with itself? Do we get -1?
Well, this is a 3 velocity. I think we get +1.
Oh, +1 in this case.
And
Yeah, like treating these as ds basically. That makes sense because it came from here.
yeah, and I think we would derive that. Oh wait, so maybe these should be s's, because what they did is they took this equation, divided it through by ds squared, and found that it
Yeah.
equals 1. And so we'd actually want to say these are all s's. Otherwise it wouldn't be normalized to 1. That's why s is a nice parameter, I think.
Okay. Okay, so now we get this times this.
And then it'd be times g, like the phi component, I think. But that's where things keep getting screwy.
So we're getting r cubed times sine cubed theta
Yeah.
times d phi ds. Oh,
Yeah.
so maybe we have to somehow relate the phi ds back to being in terms of r and theta. Oh man, I wish I knew Kepler's laws a little better and all this stuff. And angular momentum. Good grief. You know what happened? We bailed on Moore and Blue textbook a little early.
Yep.
There was a couple more chapters there at the end of the Moore and Blue book that we had to get under our belt.
Yeah. But then in example 8.7, they say just to take the tangent vector u equal to just the derivatives and don't worry about any coefficients. That's how they don't get an r cubed in their thing.
Yeah, what did they do? They said the components of the tangent vector are d. Yeah, but isn't that what you did? Oh, wait.
No,
oh, I see.
they just chop off the coefficients.
Don't put this in. Oh, you're saying don't put these.
I don't get how it's normalized then, but yeah. Oh, it's normalized because of the dot product adds it in for us. Oh my god.
I don't get it.
Oh.
Is it?
It's because when we do I made the same okay, when we do u.u, I'm mad at myself here. We only want the derivatives here because these coefficients are going to come from the definition of dot product. Like,
oh,
they come from the g's.
Are the g's.
So we only get it it's normalized if the u looks like that because we include the g coefficients from the... Oh my god. Okay.
Okay. Well, that's a little nicer.
Yes. So we get something that theoretically should be right. We need to know what to do with it next, but oh my god, this is so... I hate that I have to relearn the dot product for this. And that we engineer everything else to work around it. Is equal to some constant that they called L.
Oh, L is a standard symbol for angular momentum, I think.
Oh.
I think it's usually capital L, isn't it? I don't know.
In example 8.7, they said lowercase l.
Oh, okay.
They probably, if they use capital, that interfere with Lagrangian, I guess. Okay, conservation of angular momentum.
Where would this show up in the picture I drew? R squared sine squared theta. Where's r sine theta here? If the particle's sitting here, this is r. So r sine theta would be this, wouldn't it? Oh, the distance from the z-axis. I think r sine theta is the distance from the z-axis. Ooh, that's starting to make sense. That's starting to make sense.
Okay.
Okay, you see what I said there?
I don't understand the significance, but r sine theta is the distance from the z-axis, yeah.
Yeah, let me redraw this picture again. So if the particle's here, this is r, here's theta. So this side here, I think, is r sine theta. We could call it like, I don't know, dz, the distance from the z-axis, right? In other words, that's how far my planet is from that z-axis in terms of r, right?
Mm-hmm.
And so what do we got now for L? We've got L is dz squared times the time rate of change of theta, which is like how fast the angle in the xy plane is changing. It feels like that's something. So So if dz is bigger, we're further away and we should be going more slowly. The angle should be increasing more slowly. And if the dz, and if I'm down, here somewhere, like close to the z-axis, then dz is very small, and then the d phi ds has to be a lot bigger, right, for this whole thing to be constant.
Yeah.
So then I'm moving quickly. This feels kind of good. I mean, it feels, at least it seems to make sense.
Yeah, like it's the right track.
Yeah. I think we probably want to work out how to get it in terms of, I mean, if they've been leaving things in terms of s, I feel like they want to get everything in terms of something else. I don't know. Maybe this is good enough to run with.
Wait, so in 8.7, they take L and they insert it back into the line metric and integrate. But that's not so simple here with 3 dimensions. Unless we're holding theta constant. But even like that's getting a geodesic. Like that's what they're after in that example. We want conservation of angular momentum.
Yeah, I'm treating that theta as a constant in this picture.
Yeah.
What is S again? S is telling me
it's like your arc length along the parabola or ellipse.
It's like a little arc length, isn't it?
Yeah.
So d phi ds is like, how quickly is that n being swept out as the arc length changes? Yeah, I'd love to be able to write it in terms of time, or in terms of linear velocity or something.
Okay, you're saying that it's MRV.
Yeah. Or I think we're just going to do RV because we don't have M here. Maybe we should have brought the M somehow from the Lagrangian. I don't know.
Or I guess,
anyway,
or
it
we
doesn't
can
matter.
find, like, it's always a constant, or we want to get some type of derivative equals 0, so we could always multiply through by M after.
Yeah.
So R cross V, or just, like, if we took, is the V what you wrote the same as RU?
I don't know. I mean, I think it kind of should be.
I think so. Um, So I guess what I want to do is like take the last thing I wrote, the r squared sine squared theta d phi ds equals L. Mess with it so it looks like angular momentum somehow, and then take a derivative to get rid of the constant on the right side.
Yeah.
Phi is the angle. Oh, okay, no, yeah. Phi is like omega.
It kind of looks like MRV, doesn't it? Or it looks like R times V, because you got one R here already in the R squared. This R squared, we can break it up into like one R, and then R d phi ds could be the V, right?
Yeah.
It kind of feels like a distance times a velocity.
And sine squared theta, for this sake, is just a constant.
Yeah, wait a second.
And then we could do, I don't know if d by ds is the proper derivative here. But if theta is a constant, we can say the derivative of that is 0. And then multiply through by m. And the m could even come inside too.
Yeah.
So I think that's maybe the answer.
And sort of trying to say like this is basically like V in some hand wavy kind of way.
Yeah. The choice of S is what I'm not really sure about there. But in some ways, like there should be a relationship between S and time.
Yeah.
So I don't know. Like I don't have a better idea. Do you want to check the answer, or do you have something else?
No, I actually like what you just did. That's pretty cool.
Okay. I'm really spitballing.
I doubt if we got it perfectly, but I think we're on the right track. You know.
Oh wow. Okay, so the entire answer is right here. Rotations.
Okay.
Since L doesn't depend on phi, dl d phi dot. What?
Oh, they didn't do a killing vector. They did something else.
Yeah.
It was a bloody one-line answer.
Yeah. I cupped it. Thanks for the follow. It's a DLD feed dot because the other component, well, what happens to the, there should be a DD sigma on the left side, or like a minus DD sigma right there. Maybe they're just ignoring that for now. DP dot.
Yeah, how'd they get this? How did they get that?
They took this Lagrangian. They took the derivative with respect to phi dot. So they get mr squared sine theta phi dot.
What happened to the sine squared?
Yeah. Surely that's an error. Let me find the thing.
Yeah, I feel like that should be sine squared, maybe. What is that exponent at the end of that R cross X? Is that
The
a
Z component, I think.
Okay.
Wait.
What is that upside down delta? Is it called a del? It has lots of
Uh,
names, doesn't it?
yeah, I feel like there's not one super agreed upon name, but Adele is what I usually hear. There is no correction to 8.7.
Maybe del, or isn't it also called
Like,
nabla sometimes?
I feel like I've heard Nabla also. Let me.
Maybe it depends on maybe it depends on the problem.
Oh, Nabla is the symbol. Del is the mathematical operator associated with it.
Oh.
So Nabla is like a language thing? Question mark? And Del is a math thing? I feel like textbook writers don't care about the difference. I think Nabla or Del are both acceptable. I feel like Del is the one that I've learned or like heard more. Yes, that's a pretty common theme that we do a bunch of work just to read like a 3-line answer from the textbook.
Ugh.
Uh,
Yeah.
so, well, how are they going from?
I got a question, Don. At the end,
Yeah.
by the time we're done with all this, we have to start. We have to start like planning our revenge on Dr. Cook, right? We may as well start. We'll start planning it now. Yeah.
What's something
We got
terrible
to
we
get
can make
back
him
in
learn? I don't know. We'll have to think of something.
Yeah.
How are they claiming R squared sine or sine, like, how is this R cross X the Z component? Or X dot?
X dot is the velocity. So R cross V. So that does make sense. That's talking about MRV in the around the Z axis. So that is angular momentum around the Z axis.
Okay.
I think that makes sense. That would be what that's all those symbols are kind of standing for.
I'm trying to reverse engineer whether it should be sine or sine squared.
Well, I think it should be sine squared.
It does seem like from where we came from L, that it should be sine squared. But if we did make this sine squared, does this last equality still make sense? And does it not make sense right now as it's written? And honestly, I'm not quite sure.
We said r sine theta was the distance from the Z axis. Ah, maybe it makes sense. Oh, wait a second. Does this make sense? I don't know if I can see how it makes sense, but I'm trying to look at the picture here again, the ellipse that I drew.
Mm-hmm.
Yeah, let's look at that ellipse again. What if I draw the ellipse? Let's say the particle's here, moving this way, velocity. I'm trying to make it bigger so I can draw a better picture. This is the r. That's the r vector. Here's the v vector. If I want to do r cross v, this angle here is phi. What I want to think of is the component of v this way, don't I? Like I don't want the whole of v, I just want that component at right angles here. So I could call that like v at right angles or something. The question is, what's this angle here? Is there a reason that angle should be the same as phi? If this is a focus of the ellipse. The center of my coordinate system is at a focus of that ellipse. So if I take a tangent,
doesn't V always
the
point
velocity's
tangent?
well, yeah, the velocity's tangent, right?
Oh, yeah, you're
so
at,
this velocity that
shouldn't,
one's on a tangent line to the ellipse.
oh, with an ellipse it's not always right angle. With a circle it is. Okay, I see what you mean now.
Yeah.
So but it depends where we're on the ellipse then. Maybe that's okay.
Okay, well, let's think about that. If I'm
Like, because if
obviously
we're
if I'm
like
at
over
if you're
here,
at an
it's already
extreme
a
point,
right angle.
yeah, exactly. And so then the velocity is already at right angles, so the component of the velocity is the same as the, and what would that mean? That would mean, what would that mean? Well, then phi would be 180, wouldn't it? And what did our equation have? Sine of theta.
Hey, theta would be, I guess it's kind of, it'd be like negative pi over 2. I mean, that's kind of weird. Maybe it'd be just pi over 2 because of the way spherical works.
My picture sucks. My picture sucks. So let's try and, so if you got an ellipse, let's draw it like this for a second.
Okay.
There's two foci, right? Here and here. The way it works is that if you come, how does it work? This distance is conserved. So whatever point I pick on the ellipse, the sum of the two distances from the two foci will be constant.
Yeah.
So there's all kinds of cool properties about conic sections that I don't know.
Same.
So if I try and draw a tangent line there, why did I pick that point? It's just awful. Another one. Let's go over here. So if I come this way, so I'm interested in this angle. Here's phi. Here's r. Oops. Oh, sorry. I managed to come off the X. Oh, here we go.
Oh, I don't know what you did.
Sorry, I closed.
Oh,
The
okay.
wrong button. I'm coming back to Excalibur. Give me a second.
Okay, no worries.
All right, I think I'm back here. Oh, I don't know. Probably not worth worrying
Okay.
about too much. Yeah.
See, I don't know if what we
Probably
did is
something to
also
think
good.
about. Something to
Uh,
think about another time.
yeah.
I'm just trying to. What I'm trying to do with the picture is I'm trying to see how we get from our phi ds to r times phi ds. I'm trying to think of how to change that into like linear velocity,
Oh, okay.
magnitude of like linear velocity. I don't know. It's something I don't know how to do right now.
Me neither. Oh well. I guess we'll call it there for this group. Uh,
Yeah. What do you think? Is that enough? Chapter 8 then?
I guess so. What's going on with chapter 9? How long is it? Go from 186. Because chapter 9 I've had in my head is maybe like the last one that we'll do.
Okay. Well, it's longer than
To
8.
215. So that's like 29 pages. Which is not a short one. I might need an extra week to do it, but I'm still down to do chapter 9.
Yeah.
We can see how far we get, but like I'm going to prioritize getting through the complex analysis stuff, but if I have time, I'll try to get through chapter 9 by next Saturday.
Yeah, sounds good.
And if
Yeah,
not, maybe
in
we
here.
can just do early questions or just take a week off for GR.
Okay.
Okay.
Hey, have you looked at the have you looked much at that visual complex analysis book? I know you said you read one part of it and you didn't like it that much.
No, I haven't read anything after that.
Yeah.
Just about
I
branch
think I
points.
was yeah, that section on branch points, I just got through it. I forget when it was. I guess early last week I was reading it. And I felt like I kind of cleared up some of my confusion about branch points, but probably not all of it.
Yeah, honestly, I was just watching Slim stream before I started, and he cleared it up a lot for me. Like, why square root z has a branch point, and I'm starting to
Oh,
think about it in
cool.
terms of like maps, where if your function is, this is totally off topic, but it's still interesting. If your function is the square root of z, if you input every point on the unit circle for z, then the output is just the upper semicircle.
Yeah.
Whereas I think if I want to actually do this by hand at some point, if we inputted a circle that's like up in the first quadrant, it should stay the same. And I think that's what makes it a branch point. Like maybe it'll be resized, but it'll still be a circle.
That feels right. Yeah.
And so I
Yeah,
want to investigate
that's
that more by
yeah.
hand, but yeah.
Yeah, he did explain it that way. Yeah, he had a couple of really cool pictures. I don't know if you saw those weird pictures. He showed one where he had three different way. He was talking about cube roots, and he had 3 points that were in the uh, W plane that were the cube root of the complex cube roots of a point in the Z plane, and
Oh.
then he was showing like paths you could take around the Z plane and the corresponding paths in the W plane. It's really kind of cool. Yeah. But the reason I mention it is because boy, it's a good book, and I'm kind of like recommending it to you. It might be worth looking at some point if you want to. I don't know how much longer you got to go through that other book.
I mean,
I
yeah.
guess you don't have a lot of time left, right? I mean, the summer, we're in July now.
Yeah, I don't have that much more time, but I definitely would
Yeah.
like to supplement with VCA if I can.
Yeah, I've been enjoying it. It's got some really cool stuff in it.
Okay.
I'm up to the chapter on Mobius transformations now. It's only chapter 3, but it's really cool stuff so far.
Oh, neat. I like, yeah, our book hasn't even talked about that. It might be in a future chapter from reading the names of them, but I'm not even sure about that.
Yeah.
Oh well.
Well, anyway.
All right.
Anyway, this was cool.
Good meeting.
Yep.
Thanks for being here.
I guess I'll catch you next week.
Yep. See you.
All right. Thanks.
Okay. General relativity, as it turns out, is not easy. Who would have thought? Just give me a minute to switch things over. I don't know what playlist. We'll use that playlist. Uh, yeah, for anyone who's new around here, I sometimes do reading groups that are like these group study sessions. But my normal shtick is I do math help from anyone who wants to ask a question. And so that's what I'm about to switch into now. Any digital signal processing? In SBs, sorry, I see your comments. I have not. I think Merriweather or Mark was studying it. I don't know if you can confirm that Penbox if you remember seeing him. Merriweather or Mark might know about that. I don't think I have. Yeah, he's the only person I can think of who maybe has done it. Maybe? Okay. I think I remember seeing him doing a few streams about that. Oh yeah, the branch cut thing wasn't the focus when we were talking about it at Slim's stream. It was more just like a side discussion. We'll be to talk about chapter 9 next week and end this group after 2 meetings on that. It's a long one. My priority is complex analysis, so we take a week off of GR. Or gone the early problems. Chapter 9. Depending on progress. Okay. The reading groups don't have that much longer in them, which is by design. Am I mostly self-taught? No, I have a bachelor's in applied math. I will say I've self-taught myself a lot of stuff, but I wouldn't say mostly. BCA is a fun book, though some parts require some effort. The pictures are cool. He gives really good intuition for several things. You will enjoy the non-Euclidean geometry parts. I mean, so far I haven't been super enjoying the non-Euclidean stuff. It's cool to know, I think. Oh, hey, Fembox. 1 minus 2m over r? Oh, wait, we maybe seen that before. Wait. Well, did we do an orbit? This bad boy looks familiar. Schwarzschild metric. Do we learn about the geometry of a star? The Schwarzschild radius is when it becomes a black hole. Right? You're gonna say it becomes a black hole, right? Yeah. Yeah, they did. It's funny. They chopped off maybe the last dimension for us. Yes, but yeah, I'm getting there. So I love the mission of VCA of teaching things visually. I think it would really work for me. It just was way too long to be able to fit into a reading group. So it would have been my first choice of books to read though. Hardle is a brutal master. I mean, it was more tedious than hard, that question. Okay. So A is equal to the 2 by 2 identity minus 2m transpose. M is 2 by 1 such that m transpose m is I1. We can transpose each side of this equation to get that m transpose is I2, which I think we're gonna get a pretty boring matrix out of this, aren't we? Well, actually, is this as simple as transposing both sides? Maybe this isn't true. Because the transpose of I2 isn't of I1 isn't I2. Yeah, this is like a left inverse, isn't it? There should be something like that. I don't remember how those work. It's been too long now. Yeah, I might be smoking something. We could potentially figure out, we could potentially transpose each side of this equation and then transpose it back at the end. I need to verify certain properties about transpose. What's the actual question? If lambda is a real number, find the eigenvalues of A. Yeah, that's the shoes and socks. So is like the transpose is linear, right? A plus B transpose is A transpose plus B transpose. Yes. And I think the eigenvalues of A equal, do they equal the eigenvalues of A transpose? There should be a relationship. Hey, Armand. Okay, yeah, the transpose does not change the eigenvalues. Okay, so we're currently working on SB's question. Ved, we can talk about flux. I don't know it that in depth, but yes. Armand, yes. What's your question? So I think we want to transpose both sides of this equation. Please speak English, Ved. So if we transpose this, maybe I should break that out because I don't know. If I take each side of that equation and transpose it, we get I2 minus 2mm transpose transpose. The transpose, we can like basically distribute it to each of these things, but we do have to be careful. So I2 transpose, that is, oh yeah, we can actually, that's gonna be just I2 because it's the identity. It's symmetric. And then we have in parentheses 2mm transpose transpose. So we have to deal with this. The 2 can just come outside. It doesn't matter. I don't know how to do that, Armand. I'm sorry. For the MM transpose, we have to use shoes and socks. So shoes and socks is AB transpose equals B transpose A transpose. So we have to reverse the order. So we get M transpose transpose, M transpose. But 2 transposes like cancel it out. So I2 minus 2M M transpose. Ved, speak English. I need to translate this. Okay. That's nothing bad, at least. You're calling 1 and 3? Let's see. Because we know now we can use, now we have MM transpose. Okay, but please just speak English. Because that it worries me to see not English. What's the check we have to do to transpose both sides? Do we have to do a check? I thought we're just allowed to if two matrices equal to each other, then their transposes are also equal. I don't think there's an issue with this. Taking the transpose of each side. I'm fine by doing anything new. A transpose equals A. Well, the thing that I thought would be new is that we have this. But that does mess up our dimensions. Do we have to... Why did our dimensions become bad? Like, this is 1 by 1. Oh, wait! Oh, dude, I fucking... Yeah, we don't have this. I'm sorry. We still have M transpose M. Sorry. Fucking hell. What went wrong? Shouldn't I have gotten... Shouldn't I have gotten M transpose M by transposing this? Yeah, this is definitely what I expected. Okay. Uh... So did the thing is this not helpful then? Do I work? I do some tutoring, but I don't do much work. Chiffre. I'm not a teacher. Ved, speak English. I can't read what you're writing. Okay, I guess we'll just take m equal to uv. Young Lane, I guess so. I want to get through this question first, and then that is asking about Gauss's law, and then I'd be happy to talk about yours. Okay, and then uh u v u v is equal to 1. So u squared plus v squared is 1. Oh, thank you. Uh, Still missing a 2? Oh, ha. Yeah, the 2 gets multiplied all the way through. Okay, what do we get out of this? Pain? Misery? One minus 2v squared minus lambda. Yeah, same as b. Misery is part of life anyway. Tragedy is plants unless there's a witness who can laugh about it. Cool. Hopefully you all are laughing about this, especially when I randomly flip a sign for no reason, like I just did right there. So cancel, cancel. U squared plus v squared is 1. That's going to be important sometime. Sure. Hopefully. Maybe. These two. Minus lambda, minus lambda. are. What happens with these two? Did I count for all my terms? Yeah. So that's one, that's one. So 1 minus 2, that's all, is minus 1 plus lambda squared. Minus 2 lambda plus 2 lambda is 0. So lambda is plus or minus 1? So the sum of those squares is 2? Okay. I guess that's how you do it, SB. You were also asking, we can multiply m on both sides to get a value of lambda. Why is that not sufficient? What are you multiplying m through? Like maybe on that equation? Or I don't see what your idea is there. So we need to notice the identity is mutually diagonalizable with any other matrix. Yeah, I don't know what you mean by that, Slim. You want to multiply m through on that equation. I don't see how we would get an eigenvalue immediately. I guess, are we right multiplying m? So we would get am equals m minus 2m, and then m transpose m is 1. Multiply m and match the coefficients. Okay, like you're saying that this am looks a lot like that ax, because m is 2 by 1. I'm still struggling how you bring it home, like what you do after this. So we don't necessarily know what m is, right? This may be a bit less work though. Is it? We can't do it. Yeah, I mean, I don't really know what you do after that. It's a neat little thing, but I don't know how it's helpful. Second part, you get the eigenvalue minus 1. Oh, I see what you mean. Just the negative sign in front means that's what the lambda is. Oh, okay. That I see what you mean now. Yeah, duh. That's valid, yeah. Once we know one eigenvalue, can we get the other one easily? I forget my rules for matrices, man. There's so many. That is definitely clever. You know, if we... I wonder if we get the other one by left multiplying by m transpose. Well, no, that... left multiplying isn't it. Because we're not going to get am. I mean, with prior knowledge, we could guess and multiply through by negative m also, and we should get positive 1, but like, how would you know that if you didn't already know that it's 1? Multiply by an orthogonal vector to m, you get the other one. Really? Oh. Wait. Yes, because symmetric matrices have orthogonal eigenvectors. Oh my god. Although we only knew that after doing a bunch of tedious calculation, right? I don't know. That A is symmetric. Or maybe if you're smarter, you can just notice it somehow. I don't know how we find the orthogonal vector. Yeah, freaking the heavy linear algebra knowledge. It's got a channel string. Let m be orthogonal to v. AV is IV minus 2m m transpose v. You know the other eigenvalue. M transpose v is 0? Ah. Wow. MTV. True. Okay, yeah, SB. Wow. That's amazing, Slim. So yeah, SB, if you wanted to do it this clever way, you have to be if you can work out that A is symmetric, a symmetric matrix has orthogonal eigenvectors. So what you do is you give the other eigenvector a name v. I guess it has to have enough eigenvectors for this to work, but it's symmetric, so it does. Well, symmetry isn't enough. Because you could have all zeros. That's symmetric. There's some technicality where it maybe doesn't work, maybe. But it should for this one, for this problem. Just let v be whatever's orthogonal to m. And then multiply through on the right by v. And you know that MTV is 0 because that's a dot product. So you get AV equals V, and that now you do the same trick and you get that lambda equals 1. Oh man, Slim, that's awesome. You don't know what eigenvectors are? And you're learning eigenvalues? Bruh. You're being taught linear algebra in some fucked up way. Okay, then No, that's not your fault. If you have, so it's normally, rather than calling X a matrix, I'm used to calling the X a vector, which is just a matrix with a special size. The X is the eigenvector, the lambda is the eigenvalue. That's basically it. But if you're not allowed to use those, then I guess you have to do it this long way, unfortunately. How do you teach eigenvalues without eigenvectors, man? And so there's a whole bunch of properties that I use that you wouldn't have learned about yet then, with symmetric matrices and stuff. Okay, Ved, are you still here? Do you want to talk about Gauss's law? Thank you for the question, SB, and thank you for your patience as well. You know the properties? Okay. Okay, Ved, if I don't hear from you soon, I'm gonna skip to Young Lane's question, if they're still here. So yeah, Young Lane, feel free to tell me what your question was. Because I'm not hearing anything from Ved yet, so. Is the question just to solve that? It's from Alan Wake 2. You have to solve this in Alan Wake 2? I've heard of it. I have not played it. They make you solve... That's kind of funny. Oh my god, Fembox popping off. You just did that in your head? Okay, I like using elimination for these. And so, we have an X and a Y, a 4X and a 2Y. So kind of the smallest common thing I can see is to get 2 Ys. So let's take this equation, multiply it through by 2. Easy to do when you don't get it right. Ugh. Yeah. You just said to answer the question, not answer it correctly. Gotta be more specific. So yeah, I want to make the y's match up, and then I'm going to subtract the equations. So 2y minus 2y is 0. 4x minus 2x is 2x. 754 minus 400 is 354. Now divide each side through by 2. 1, 7, 7. Yeah. You got it right. And so if x is 177, we can plug it into either one of these. The first one is easier though, because the numbers are smaller. So that's going to become 177 plus y is 200. Subtract the 177 over, you get y is 23. We don't have eigenvalues in the syllabus, therefore we don't solve. Knowing we're finding the eigenvalues. Oh, okay. That sounds like a terrible way to learn linear algebra. I've got to be honest. Maybe there's a method to the madness there, but I don't see it. Yeah, young lady, when we said it was from a game, I think like you invented some type of game and I'd have to like analyze what the best strategy is. I'm glad it wasn't that complicated. Although I would have tried that too. Hardlocked? Hey, first, you sure are. An inch of time is an inch of gold. Measuring time in inches. That's like what we've been doing with general relativity. Yeah, exactly. We could talk about you get a mile of time. That's the thing that we're actually doing in physics. We're measuring time and distance. And you think of it as like if you have like 2 miles of time, it's the time it takes for light to travel 2 miles, is how it's been interpreted. Star Wars measures time and distance, do they? Wait. When do they do that? Okay. So we might just do some general studying. I don't think anyone's posted anything. So maybe we'll do complex analysis. Remember? That's because Thinlock's fan is just a superhuman. He did it without a calculator too, I promise you that. It's not what algebra, it's called just matrices. Just an introduction. Just hand out the Cayley-Hamilton theorem? Oh wow, that's crazy. Yeah, young Lane, like the people who show up to master rooms, like the people in chat, are like way smarter than me. Yeah, I've heard a lot of complaints from the Indian people who come by in chat. At least I can't say I know the system much for myself. I think 4 is probably a good one. Oh, there's a sneaky part C at the bottom there. Didn't even see it. Did I start running residues too? Yeah, I've read through nearly all of 4.1. It's so weird how important series are. Because, like, so the residue is just the C sub -1 coefficient of the Laurent series. But you can do all these things with it. And also you have to find that in the first place. So we probably want to do a flipperoo. One over 1 minus z squared is equal to the thing that we have. Is it taught as linear algebra from the start, like matrices is a part of linear algebra in the US? Yeah. You normally learn about those two things at the same time. So the idea of being taught them separately is very odd to me. Probably need to factor out a negative. Oops. Okay, I hope that's good enough for a discussion of the continuation of the following function. So with part B, it does, yeah, it looks like the integral of a geometric series. Well, they do it as a definite integral, maybe just to avoid any issues with the constant. All right, B is a little more spicy. I think India is the most popular country that watches my YouTube channel, yeah. I wish you guys had an easier university entrance exam. Yeah, I looked at the stats on YouTube. It's like, I think like 50% last I checked. We can check again because I'm kind of curious. Where is it? Yeah, here we go. Oh no, it's not 50. 35% India, 9.3% US, 2.1% UK, 1.5% Bangladesh, 1.4% Canada. So, yeah. Over on Twitch, I think it's more US and Europe, though. I think Twitch is mostly US. Actually, you know, I kind of look at it for Twitch too now. Let me find where it is. Engagement, maybe? Discovery? Okay, yeah. US, 43%, UK, Canada, Germany, Netherlands, Philippines, Portugal, France. Actually, for some of these smaller ones, I think I just know the people who are watching from those countries. Like Portugal is probably like Mouse and like I think maybe one or two other people who I can think of. GP Bear. Can you explain how the gamma function normalizes around negative integers, like why minus 1.1 is continuous, but minus 1 is asymptotic. I don't know the gamma function that well. Maybe we can figure it out. I don't know the answer to that offhand. When you say normalizes, do you mean like the gamma function just like works and gets a value? Wait, you're saying non-negative integers, but then you talk about negative numbers. Do you mean negative integers? You meant negative non-integers. Okay, okay. Yeah, so it's weird as it has those asymptotes at negative integers. There's a 90% chance this is a rickroll. I'm gonna click on it anyway, though. What the hell? Wait, open it. Stop. I keep pressing Shift Enter. It's opening it in a new tab. It is a rickroll. I called it. Oh man, you did the clever thing too. You didn't get the big video, so it only has 500 views. Like the one with all of these has like, I think it starts like XQ or something like that. um oh, neat. Okay, so what this part of the Wikipedia article is saying I definitely have people try to rickroll me. I think it was Jed who's tried also. People have definitely tried to rickroll me on stream before, though. So what they do is you start by making the gamma function work for all positive values. And then once you have it working for all positive values, you can make it work for negative values. It relies on this thing called Euler's reflection formula, where gamma of a negative number is equal to 1 over gamma of a positive number plus 1. But it's this sign thing that causes the issues, I think. Because if you plug in really any integer x, you're going to get sine of 0, because sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0. Same with negative pi. And so I think that's why we get the asymptotes at negative integers. So we just get a 0 on that Euler reflection formula. Hey, shortifies. Yeah, the username is also a red flag. It's even a red username to match the flag color. So yeah, that's kind of interesting. Where I knew about Euler's reflection formula. It's an important thing when it comes to gamma. I didn't know that that's what uh I didn't know that's the reason for the asymptotes though. So I don't know. I hope that helps, GP Bear. But if this is, I'm not sure what your like background is, so I'm not sure if I'm explaining it in terms that you know. You're Sanvi Verma. You're from India. You're preparing for IIT JE. Tips. I have a hard time giving tips for that. The questions, JE questions that I've tried have been very difficult for me. It seems like JE is a very, they do things a very particular way that just isn't really taught here in America. So I have a hard time giving you tips. I'm sorry. Yeah, I've tried JE questions before. The mains I can usually do, but the advanced ones are just kind of ridiculous. Okay, so yeah, GP Bear, if you want to hear me try and say this in a different way, or if you have a question about what I've said, let me know. But if I don't hear from you, I'm gonna go back to doing what I was doing before. That's true. We are talking about analog continuations, which is it's pretty on brand to talk about the gamma function. The gamma function is a little bit harder to work out though. Yeah, I don't know how you actually do get the gamma function, to be honest. Shortifies, it's the toughest exam that I've seen, at least. I haven't made an effort to find out about all of them, but J Advanced is probably the hardest one that I've seen. I'm confused if we want to go to the integral representation immediately or not. Um, Memorize patterns. That seems like an important piece of it. Well, I guess we need to remember the analytic continuation for geometric series for z greater than 1. So if we have 1 over 1 minus z, we can factor out a minus 1 over z. Okay, and so we're going to take this series and send it somewhere else. That's a 2, not a z. requirements to get admission in MIT, but I would look at their website. I don't know. So this integral is gonna be a little bit funky. Because when n equals 0, we have 1 over z. So that's going to be log z. You also preparing for JE? Oh, well, good luck. So, but then everything after that will be okay. Do all the signs flip? I think they do. So it's going to be purely positive. So it's minus 1 over z, minus 1 over z squared, minus 1 over z cubed. This one is going to integrate to... Oops. Add 1, divide by the new exponent. Okay. And add 1, divide by the new exponent. Yeah, I like this. So that's my analytic continuation question mark. It's an even number, so I can't check it. Kind of interesting that we get branch cuts. Because of the log. Okay, and then surely z to the 4 to the n is not going to have an analytic continuation. Because z to the 2 to the n does not have one, so why would 4 to the n change anything? Okay, maybe we should try to repeat this argument just in case something changes. But I don't imagine anything will change. Hey, Jasu. You're not falling for it either? Are you all submitted now? I guess we maybe want to talk about f of z to the 4th. Like your dissertation. What is an analytic continuation? She's overdue. We don't talk about her. Okay, no worries. So SB, an analytic continuation is uh how do you describe this? It's a way of continuing out continue a function outside of its domain. It doesn't work for every function, but shortifies, please speak English. Or wait, that looks almost like English, but it's not quite English. It looks like a mix, maybe. But please keep it to English, please. So I can't read that. Oh, you did submit your paper, and that's okay. So your paper is different from your dissertation. SB, a famous example of an analytic continuation is for, yeah, it probably is Hindi. Famous example of an analytic continuation is for factorial. So normally if you want to take the factorial of a number, it can only work for integers. But there's an analytic continuation of it called gamma. And I think it's like n+1 or something like that. But gamma is an analytic continuation because it works for nearly any number. It just only doesn't work for negative integers. But any other real number you can plug in. And if you plug in an integer, you get the exact result as a factorial. Designing your math BSc studies, nice. Complex analysis time, yep. So that's kind of like the short explanation for what an analytic continuation is. It lets you use complex numbers to kind of expand the domain of functions from what they would otherwise be. Okay, so I'm talking about part C here, and the suspicion is that there is no analytic continuation for that. Because they say that z to the 2 to the n doesn't have a continuation, so surely 4 to the n won't be any different. But we should investigate it properly. And so what we've shown here is that f of z to the 4th is equal to f of z minus z. And we know that z equals 1 is singular because this function blows up to infinity if z equals 1. But during BSc, there's also mandatory language studies. So you have to study some other language. Really? Like, if you already know English, and presumably you already know Finnish, like, you already know 2 languages, they're going to make you do a 3rd one? Finnish, Swedish, and a foreign language. That's what they make you do? Wow. It's a lot of languages. Can use your degree to get out of it. Okay, good, good. I feel like if you're coming around for a second bachelor's, that you shouldn't have to do like a bunch of general ed stuff. um, yeah, that is a really cool thing, SB. I'd love to know more languages than just English. Yeah, those junk general courses in undergrad. They're definitely something that honestly, yeah, I'm a little bit I didn't really like doing the general ed courses in my undergrad, but people do. There's an argument in favor of them. I am a little bit like undecided about like if they should really be required or not. So I'm looking for Finnish and Swedish. Oh, degree in the UK had no language component. Oh, okay. I don't know why you would need a language component though. UK degree had no general ed part to it. Okay. Wait, did you do... So I know you're doing your PhD in the UK. Did you do like all your degrees before that in the UK also? Okay, that makes sense. Okay, so between this fact and the functional equation, this means that all the fourth roots of unity are also singular. You did a 4-year integrated master's course before your PhD. Ooh, okay. Integrated master's course, like integrated with the undergrad or integrated with something else? Yeah, I had the same question. BSc plus master's. Okay, fair, fair. So fascinating. People from so many countries can just speak to each other in real time now. Yeah, that is awesome, SB. Like we get people from, I guess not all parts of the world, but a lot of parts of the world. Like I don't think I've had anyone from like Africa who I know of in the chat, but still quite a few countries who are represented in some way. How do they continue the argument after this? Oh, right, you square that. Understand the world of quantum gravity? I sure do not, Empire. What time is it for me? It's 4:45 in the evening. 4:46. You only get 1 degree at the end instead of a BSc and a master's. Oh, that's weird. Saves you a bit of time though if you do the entire thing in 4 years, rather than a 4-year undergrad and 2-year master's. $16.46. I'm not used to using the 24-hour time. It is just better, but I always have to. It takes me a minute to subtract 12 to figure out what It's what the time is in the time that I'm used to. And I do it wrong like half the time. I don't do math every day. I'd say like most days. I don't have a particular um amount that I do it though. I just set a goal for myself and I'll do as much as it takes until I get there, basically. Okay, see you, Ved. Resnick Halliday. I've heard of that book. Concepts of Physics by H.C. Verma. No. Iridov in Physics. I've heard of it, Iridov, I think. Hey, Nikhil. 5:20 a.m. in India. Didn't sleep at all. Oh, no. Hope you get some sleep. Okay, so this shows us all the eighth roots of unity are also singular. Are we going to get to every root of unity? I kind of... I think... Should not sacrifice sleep to study? Yeah, I agree with that. Sleep is extremely important to having like a functioning brain. If you the questions are too easy, then yeah, you should probably try to go for harder ones. I I usually when I study, I try to go for questions that I struggle with because that's what I need to improve on the most. So I guess yeah, I usually go for the hardest ones. Is the US one day ahead? I think the US is one day behind. For me, it's Saturday. Oh, I haven't seen a table like that, Jasu. I've heard that, like, in general, like, you know, they're being sleepy is as bad as being drunk, depending on how sleepy you are. Actually, yeah, well, let's see. Sleep deprivation versus intoxication. Being awake for 17 hours is like having a BAC of 0.05%. 24 hours is like 0.10%. Wow. It is in America. You can't drive if you're at 0.08. Um, wait, so does z to the 2 to the m truly capture all roots of unity? What about like z cubed equals 1? Are those captured somewhere down the line? Did quantum physics without sleep for 24 hours once? That doesn't sound like a very good idea, Empire. Oh, collar cone, you finally proved the proposition you were stuck on for the last 2 weeks? Hell yeah, that's huge. Don't all-nighter for exams that is almost comparable to showing up drunk? Yeah. College needs the entrance exam to be hard. How hard is it if you compare it to the US entrance exams? Uh, no, from what I've seen, JE is just it's literally harder. There's probably also a difference in teaching style, but in America we have the SAT and the ACT, which when you take depends on like where you're from. The math that they ask you to do is not as hard as they ask you to do on JEE Advanced. In America, we really don't have an equivalent for the JEE Advanced that I know of. JEE Mains is probably about similar. I did the SAT. I don't have very good tips though, because when I was in high school, I didn't give a shit and I didn't study for it. I remember in high school being able to do the PSAT, like the practice SAT for free. That's definitely something to take advantage of. But other than that, it's like just look up resources online. I'm sure that there's a million of them. And I should have studied. I just in high school, I just didn't care. That was the last hard thing in your master thesis? Hell yeah. That's awesome. Jesse with the painful laughter. That's how I'm interpreting it, at least. Honestly, another is, again, I'm not necessarily convinced that this does get all roots of unity, but I'm kind of getting tired for the day. Does it matter that much if you don't get good marks in SAT or ACT? It does matter, but you can make up for it. In America, it's pretty big to have like they call them like extracurricular activities. Like sports can really help you out. Being in clubs can help you out. Yeah, but I thought I replied to it for which books that I've heard of. Resonant Calday I've heard of. Concepts of Physics I have not. Iridov I've heard of. I don't know anything about. Physics Galaxy I haven't heard of. But yeah, so they consider kind of your entire application and you as a person, not just purely your GPA and your SAT score or ACT. But if you want to get into like the elite colleges, you need to have everything perfectly. For EU, at least it varies by the country, I'm sure. I've heard from some people that they only consider your grades, though. I think I'm going to start wrapping things up, though, here. I think the point is that you have a dense subset of the unit circle. Okay. Yeah, it seems like a little more subtle than they're making it, but... Okay. Thank you for commenting on that, color cone. Quick question. Yeah, what's up, SB? Did then just not get enough applicants? I don't know, Empire. I don't imagine they have that issue, but I don't know how it works over there in particular. Usually grades, possibly personal statement. Okay. For the version of the question that they asked in part C, then I think we'll get the same thing with z to the fourth. Like I assume that'll still be dense. A dense subset of the unit circle is a nice way of putting it. From with UK, France, Belgium, and Finland. Okay. Storyline helps a lot for an essay. Oh yeah, true. So I don't know. I don't feel like writing out the last part of the argument because it's really just copying and pasting the book's argument, I think. My brain is a dense subset of my body. My brain does. Well, wait. Now, at first I interpreted that as you having a lot of brain matter, so you're really smart. But then there's also like the British, like if a British person calls you dense, that means that you're stupid, right? So that could kind of go either way. I'm not seeing your question yet, SB. I do kind of want to go though. So if I don't see it in a minute, I'm just gonna cut the stream off. I'm sorry. Oh, there it is. If you give the SAT, you think you can give exam, you don't know. These are to get U.S. citizenship. If you get selected, what about other stuff like the co-curricular stuff? Well, citizenship, I really don't know the first thing about personally. Like, I was just born into mine. So I would imagine it's a lot easier to become a US citizen if you're over here already on a student visa. I know nothing about how it actually works, though. I'd imagine it's easier to become a citizen if you're already here, though. And for the other stuff, just, you know, try to tell a compelling story about your life, kind of like Empire said. Like, it's a lot easier to make that story if you do the, like, you know, clubs, sports, hobbies. But you can also be like overcoming hardship or something like that too. So there's a lot of like flexibility in how you want to like tell your story. Think about 12% of applicants got in this year solely on grades. More applicants than places. Okay. If Z is on unit disk, any small neighborhood of Z must contain a singular point. F cannot be analytic. Oh, yeah. Okay, that's fair enough, color cone. That's the important thing. That any neighborhood has to have a singular point. CSV. I hope that at least helps a little bit. I definitely... Immigration is a very complicated thing that I've never had to do. But I'd imagine that being here as a student will help a lot. But on that note, I think we're going to call it. So yeah, thanks people on YouTube for being here. Empire SB, anyone else who's lurking on Twitch will look for a raid. On YouTube, I'm just going to call it. So goodbye, YouTube.